Good morning. So, we are going to continue our chemistry journey on to Chapter 5. Chapter 5 stuff, for the record, will not be on your first exam next week. It will be on your second exam. So, just for the record there. Oh my goodness, why can't I? Make sure this is working. Cool. Okay, so when we're looking at stereoisomers, remember that when we talked about isomerism before, we learned about constitutional isomers. We had a couple homework problems where you were looking at different isomers of each other that were just atoms that were rearranged in different ways within the molecule. Stereoisomers have the same kind of connections as each other between the atoms, so same arrangement and connections of the atoms, but they're different spatial arrangement. And so, good morning. We kind of had other words that we would use to describe this sort of thing. We would say cis-trans. For example, we would say, okay, well, they're similar side to each other. There's the same connections. For example, if we had we talked about these being in this order trans and cis. Those were in relation to each other, right? We were able to say, okay, well, yeah, this bromine is pointing up, the other is pointing down. They're kind of pointing the opposite direction of each other, and therefore they're trans to each other, which is fine. But we see that these are stereoisomers of each other. And the reason for that is because they all have the same connections. They have the 6 carbons connected together, and then they have a bromine on carbons that are adjacent to each other. So the connections are the same, but they're just arranged differently. And so we're going to see that this phenomenon of stereoisomerism is going to be very common in organic chemistry. And we're going to see, in fact, these two are, well, we'll talk about what type of relationship they have to each other in a little bit. So what it really comes down to, though, is if we have an sp3 carbon, or it doesn't have to be carbon actually, it's sp3 atom with 4 different electron domains. It will lead to stereoisomerism. And another word for this is called chirality. Chirality. Yes, those are diastereomers of each other. Yes, correct, up there. If we look at a molecule, we'll see what this is. We see, if we draw the mirror image of this molecule, in fact, those are going to be the... no, we're good. If we draw the mirror image of this molecule, we're going to see, just like with our hands, hand 1, mirror image of hand 1. Yes, they are mirror images of each other. So here's my mirror. It's reflecting onto the other side. We're going to see if I try to put these on top of each other, they don't line up precisely, right? I have, or something, whatever. I have bits here that are not aligned. We call these, so here's a mirror, by the way. These are called non-superimposable mirror images of each other. So just like our hands are mirror images of each other that are not superimposable. We cannot put them on top of each other to get them to line up perfectly, as they are mirror imaged. If I flip one around, yeah, now they can, but that's cheating. So just mirror images, you try to overlap them, it's not going to work. And no matter what you try to do with these two molecules I've drawn here, if you try and rotate them and move them around, you will never get them to be identical to each other. So if we were to rotate the molecule on the right, if we were to say let's rotate this thing so that the fluorine is going to be now on the right side. If we rotate around the carbon-bromine axis, we see what happens here is that chlorine that was pointing front as we rotated around is now in the back. And our iodine that was in the back is now in the front. So these two molecules are the same, these latter two ones. I've just rotated it. But we see here that I've tried to put it where the bromine and fluorine are in that same relationship as our original molecule, but now my iodine and chlorine are switched. And so as a result, this difference in arrangement is what causes this non-superimposability, or what we call chirality. And interestingly enough, these chemically behave similarly to each other, but physically they actually do different things, which is pretty interesting. And so we're going to see that anytime you have any sp3 atom that has 4 different things on it, you will have what's called a chiral center in your molecule. And so if we take a look at this, actually let's not worry about the cyclic ones right now. We see this carbon in the middle has 4 different groups on it. And we saw that I could arrange those in different ways, where all of them are still connected to the central carbon, but I've kind of swapped a couple of them. And as a result, we have what's called a chiral center. That carbon is chiral in the middle, and overall the molecule will be chiral, and there will be different stereoisomers we can get out of it. Let's take a look at identifying chiral centers. Often we are looking at carbons, right? But you could have chiral nitrogens, for example, or something else. First things first, it must be sp3. Must be sp3, and it must have 4 different things on it. Because if it didn't have 4 different things, if it only had 3 different things, here, let's do it. If we had this one, if we had its mirror image, there's its mirror image, and if we just rotate this guy, this is now identical to our original structure. So this one that had 3 different things is not chiral. This is not a chiral molecule. There's no chiral carbon in it. So this one had 3 different things on that carbon. It's therefore not chiral. So kind of our first technique with this is identifying chiral carbons. And so if we have something like this, we might want to look at them. You might want to look at all the carbons, and it may help for you to draw in hydrogens. it may help. If we're looking at the molecule on the left, if we're going to see if there's any chiral carbons on it, we might want to draw in our hydrogens. Hopefully right away, we can see at least 3 of these are not chiral because they have 2 hydrogens or more. Like the left 2 and the rightmost carbon all have multiple hydrogens, therefore none of those will be chiral. But now we want to look at our last carbon, right? That carbon there has a hydrogen. It has a hydroxy group, or an oxygen on it. It has a methyl group and an ethyl group. That's 4 different things. So we see here that this carbon will be chiral. It will have 1 chiral center on that oxygen. Because that carbon, it's got H, it's got methyl, it's got ethyl, and it's got hydroxy. So 4 different things. So you're looking for a point of difference. So yeah, it had 2 carbons connected to it, but those 2 carbons were not identical. 1 carbon had 3 hydrogens, 1 carbon had 2 hydrogens, and another carbon. So those 2 are different. If we look at the next one, if we draw in our hydrogens, on these 3 we can see right away, oh, definitely no, none of those are chiral. How about this last one? If we go ahead and see what this carbon has, it has a hydrogen, a methyl group, and an ethyl group. So even though I drew it with a dash, which is totally allowed, I am allowed to do that, it's just rotated that way, this is not chiral because it has 2 methyl groups on this carbon. This carbon here is not chiral. It has 2 methyl groups on it. So anytime you see a wedge or dash, it doesn't necessarily mean it's chiral. So I could trick you. But it's for your own good, right? No. So it's very important that when you're looking at things, don't just immediately assume, oh, well, there's a wedge and a dash, it must be a chiral center. Not necessarily. Not necessarily. If we're looking at this, I mean, the last time it was a dash on a methyl, we're going to see indeed this molecule is also not chiral. Because if we're looking on it, I mean, mostly you can see these other ones are very obviously going to have more than 1 hydrogen, so I'm not even going to bother with any of the other carbons. If we look at those, we'll see, okay, well, we have butyl groups, 2 different butyl groups. This carbon has hydrogen, chlorine, butyl, therefore it's not chiral. Plane of symmetry is going to be a little bit different. When we talk about meso compounds, we'll see that you can have compounds that are not chiral, even though we would expect them to be chiral. But that's something we'll talk about later. Symmetry can kind of help a little bit, but that's something we'll talk about towards the end of this chapter. So, we can do a couple more. Kind of ugly. Let me fix this. I'm gonna just redraw this one because I drew the geometry terribly. if we want to think what's chiral here, we want to look at, I mean, again, most of these carbons we can kind of just gloss over. Like, okay, if they don't have anything drawn on them, they're probably not. Most of these will have 2 hydrogens. So you can see it. So there's going to be kind of maybe 4 carbons of interest here that we're looking at. Let's see if they're chiral or not. We're going to see that this carbon or this molecule will have 2 chiral centers only. Let's look at them from left to right. If we're looking at this carbon, first thing, it has a hydrogen. It's got a hydrogen. It's got this, I don't know, butyl thing. Substituted butyl. Whatever. We also have this cyclohexane bit. And we're going to see that when we're looking at if something's different or not, we are looking at kind of the first point of difference. And we're going to see that because, like, if we try and go, okay, well, let's look here then. Is this carbon the same as that carbon? And they are, right? No matter how far we go away, it's all identical to each other. And so I don't know how to write this, like half of a cyclohexane and another half of a cyclohexane maybe. That carbon will not be chiral. Because you keep trying to go away, there's no difference in the 2 carbons that it's connected to. Those carbons are each part of the cyclohexane. There's no substituents. As soon as we throw something like this on, if we throw a methyl group there, now it's chiral. But since there's no difference on any of those carbons, it's not chiral. This carbon has 2 hydrogens. We don't even need to list the rest, so that one's not chiral. The one with the chlorine, let's have a look. We have an H on it. We've got a chlorine. We've got a carbon with a bromine. And then we have a carbon with no bromine as we move to the sides. So, as a result, this one is chiral. It has a chlorine. It has a hydrogen. It has 2 carbons on it, but those carbons are not identical. One carbon has bromine, the other one does not. First point of difference. As soon as, if you're looking at carbons, and you're looking at if those carbons are identical for purposes of chirality, you're looking at your first point of difference. So if we go to the right, that carbon is connected to carbon and bromine and hydrogen. If we go to the left, that carbon is connected to carbon, hydrogen, and hydrogen. So there's no bromine on the carbon on the left. Therefore, the carbon with the chlorine is chiral. It has 4 different things on it. And by process of elimination, the last one is chiral as well, but let's make sure we understand why. We've got the hydrogen, we've got a bromine, we've got a methyl group, and then we've got the rest of this molecule. So if we're looking at the point of difference, our point of difference in purple, those are both carbons, the purples. Purple on the right has 3 hydrogens. Purple on the left has not 3 hydrogens. They're not the same. So therefore, that carbon is chiral. So far, so good. Let's see. Let's do some examples. Oh, here we go. Let's do the ascorbic acid, yes. Oh, I need more space. So the ascorbic acid that we had drawn improperly earlier. Okay. Let's see what chiral centers we have here. How many and where? Let's go ahead and kind of first indicate ones that are not chiral, that are right away not chiral. Easiest way to do that, let's eliminate all these sp2 things first. Those three are sp2, so we can get those out of the way. We don't have to look at them anymore. So if we're looking at the rest, we have really kind of three other things we're looking at. So if we look at the one on the left, it's got 2 hydrogens, so that's not chiral. If we look at the one in the middle, we have a hydroxy, we have a hydrogen, we have 2 carbons. So now we're going to go ahead and look at them. Let's look at these 2 carbons now. Are those carbons identical? No, they are not. One carbon has hydroxy and 2 hydrogens. The other one has an ether and some other stuff. And we tricked Kevin for once. It's a miracle. So this one indeed will be chiral, and we'll put a little star on it to indicate that it's chiral. It's got unequal carbons on it, or unidentical carbons. And that last one there, it's got an oxygen, it's got a carbon with an sp2, it's got a carbon that's sp3, and it's got a hydrogen. So that one will be chiral as well. So you just need to look. Tricky parts come when we are looking at carbons, like other carbon bits as our if they're identical or not. Let's see, what's another good one to do? I have just kind of one like little suggestion or note as well. When we are comparing like point of differences, we treat as 3 bonds to carbon. And we're going to see what this looks like in a sec, especially when we talk about RNS. We'll definitely see this more. And we're going to treat double bonds as 2 bonds to carbon. So if we're looking at, for example, something like this, it'll be more important when we talk about priority. If we're looking at this carbon here, we're going to see that if we look at the first point of difference, the carbon that we're looking at has a bromine and a hydrogen, and it's got 2 carbons on it, right? The carbon on the left, we're going to say that carbon is connected to 3 carbons. We kind of like pretend. And when we talk about priority, yes, the triple bond will have higher priority than a double bond will. But in terms of identifying if they count as the same thing, this one will say it's connected to 2 carbons. And so these are different from each other. You can also say, okay, well, the one on the left has a hydrogen, the other one doesn't. That would work too. But when we're talking about priority, this will become more relevant. So we'll see that indeed this this center is chiral on this molecule. All right, everything has to be identical, or two things have to be identical completely for something to be achiral. So for it to be chiral, everything has to be different. This is different. Okay? All right. Let's talk about enantiomers. When we are looking at these mirror images of each other, I think the book does a nice job of this. I did our mirror image where we looked along this axis and we got, aha, here's our molecule, here's our mirror image, right? Yeah, for sure. Shane, yeah, there's plenty of reasons we could say this is sp3, I'm sorry, this is sp2, this is sp, those are different. Yeah, totally. For sure. Or this one has hydrogen, that one doesn't. The end. So if we're just looking at if it's chiral or not, for sure it is. But we'll see later when we talk about priority, assigning priority to what different things are, then it does matter. So, but yeah, totally. Yeah, you don't have to go that far into it. You can see it right away that they're different. Easy. So enantiomers are those non-superimposable, superimposable mirror image. I put our mirror along kind of the side. That's the way that I typically would think about mirror imaging things. But we have actually 3 dimensions we could reflect this across. And so I did it to the side. We could put the mirror kind of in the same plane, just like behind the molecule. If we do that, I don't know how to draw that, but this would be kind of mirror to the side, right? If I were to put the mirror behind it, I would end up with this. So essentially, if I look at it from behind, I'm looking at it now with the dash. This is also an enantiomer. So I can go from the side, I can go from behind, or I could also go from below. So if I take this molecule again and reflect it now across this one, if I do a mirror image across that, this is also the enantiomer of this molecule. And in fact, these 3 things are all identical to each other. Believe it or not, these are all identical molecules. All I have to do is rotate them to see that they're identical. Like this one, I would just rotate 180 degrees, and now poof, I've got the molecule on the top. Or I rotate it 180 degrees that way, and now I have the molecule on the bottom. Or I flip it over 180 degrees that way, and now I have the molecule on the right. So those 3 are identical to each other. They are all the enantiomer of our original molecule. These are all the enantiomer of our original molecule. So no matter which kind of mirror plane you use, you can just reflect it across. My preference for drawing enantiomers is the kind of leftmost one here. I like doing the mirror from behind, the one that I'm not able to draw. So mirror to the side, mirror below, those are easy to draw. But in terms of like actual preference for drawing an enantiomer of something, I like to do the mirror from behind. All you have to do for that is switch all your wedges and dashes. And that's all it is to draw it. So that's kind of the way I like to do it, but any of these will work. Flip it upside down, flip it to the right or left. And so we're going to see that an enantiomer of a molecule is going to have every single... Yeah, kind of. So, do I have a mirror nearby? No. It's a new house. I don't know where anything is. So, if I had a mirror, I would be able to show you, but unfortunately I cannot. So, kind of. So, here, let me try this. Let me find an image on Google that's going to help show this kind of what I want it to show. Okay, so let's say an enantiomer mirror behind. These are all mirror to the side. Give me like behind. You'd think Google would have pictures of these, right? Aha. Oh, and I think this is in fact the one from the book. Okay. Let's see. Let me swap this over here. Yeah, that's what he does. So, yeah, the background is different, isn't it? So, I still have like nothing here yet. So, we'll get there. Okay. There we go. Okay. So this is from our book. I've lost it. Here we go. This is what we're looking at. It's terrible, but it's super blurry. I get that, but these are the three mirrors you can do. You can have a mirror next to it, you can have a mirror beneath it, or a mirror behind it. If you do the mirror behind it, that's this case right here. So if you were to stick your mirror behind the molecule, notice that this wedge here is pointing away from the mirror. And so if you put the mirror back there, it's now pointing into the mirror. We are looking at it from the other side. So we're looking at the back side of the molecule, essentially. We're looking at it from behind. I'm sorry, it's super blurry like this. Maybe if I like zoom out a bit. Nope, I can't zoom out. Okay, well, whatever. That's what I'm talking about with mirror behind. So we're looking at essentially something that was a dash becomes a wedge, and vice versa when you're looking at it from behind. So that's the difference there. So, easiest way to do it, if you have a molecule, here, let's take that, let's take this one from before that I've completely drawn over, and now it's impossible to tell what the original molecule was. Let's erase all this gunk. If you can identify your or what's chiral and what's not, easiest way to draw this. So remember we saw that these two carbons weren't chiral, so it's just like forget it. Don't even draw a dash there. Just make it a straight line. The dash meant nothing to us. But the easiest way to do it, to draw the enantiomer, is just to switch all your wedges and dashes. So that chlorine that was on the dash, on the wedge becomes the dash. Everything else stays the same. Just switch the two. In my opinion, that's the easiest way to draw the enantiomer. However, if you really wanted to draw a different reflection, that's fine. There are 3 different reflections you can do. You can do the one on the side. Here, I'll draw it. I'll be good. So here's our original molecule. If I wanted, I could just reflect it. I could say, okay, keep everything the same and reflect your molecule, and now that's the enantiomer. That's fine. In my opinion, it's easier to just switch your wedges and dashes, copy the molecule exactly otherwise. So that would be another way. Or you can flip it upside down. Do it the other way. So that one's a little bit more complicated, so I would stick with one of these 2. Probably this way. This is probably the easiest way to do it. So if you just kind of invert all your stereo centers. So switch wedges and dashes. That's it. All right, let's see. Let's do a couple of... let's do this example. All right, let's do ketamine. Yeah. One of them starts at nothing. Nothing's here. What's the question about above? What's this down here? That's a methyl group. Okay. 4 different stereoisomers. For this one? That's correct, but enantiomer-wise, there's only 1. Or the enantiomer is always a pair. We're going to see the diastereomers would be the other stereoisomers that we'll see here. Okay, 1 sec. Let me figure out what's going on here. In the meantime, you draw me the enantiomer of this. All right, Cotton, this is your fault. You're the one at blame here, mister. All right, I've captured the ringleader of the Borking operation. So hopefully this will make the rest calm down. Yes, I know you're so mad. Okay, so if we're drawing the enantiomer of this, first things first, we've got to find our chiral carbons. Or chiral anythings, but there's only the carbon in this case. So if we do that, we see that we have 1 chiral carbon, 1 chiral center, rather. And so if we're to draw its enantiomer, now Oz is going, oh my god, that's the ugliest benzene I've ever seen. 1, 2, 3, 4, 5, 6. Oh, that's so much better. Okay, and then we have on the other side. Let me go get that one. Oz, come back here. All right. So, hopefully we see that. 3 chiral centers in this. So, the first one, remember that this is... Those are all sp2 in the benzene there. So those will not be chiral. The one with the chlorine. So that doesn't count. I guess the other one might be the nitrogen. Lone pairs actually do not count for chirality purposes. The reason is... let's see. So nitrogen typically has trigonal pyramidal geometry, right? So, oh, I'm sorry. You were probably then looking at the other carbon connecting to the cyclohexane. Got it. But this is a good point to talk about as well. With nitrogens, what happens with lone pairs is they kind of behave like umbrellas. So we have the umbrella that's pushing down the other three groups, right? The lone pair there. It can also flip it itself. So things with lone pairs rapidly invert themselves. And so it just kind of just decides to now all of a sudden flip itself over. So things... these things are just rapidly inverting, so we're not going to worry about lone pairs. So don't count lone pairs as things. We're looking at like atoms, really. So I said electron domains. It would be a better, more precise for me to say different atoms or different non-lone pair domains. That's the answer. Don't consider them. So lone pairs do not count. You can have chiral nitrogen if it's positively charged. If you have a quaternary nitrogen, you can have it. If it's got a fourth R group, you can have it if it's positive. But for lone pairs, we're not going to worry about them with chirality because they just rapidly invert. So only worry about atoms. Okay? So with this molecule, yeah, we just have one chiral center, so we just need to invert that one thing, switch the wedge and the dash. And I think Kevin had pointed out over the weekend, if you had something like I don't know, something like this, both of those carbons would be chiral, the ones that have the substituents on them. Both of these are chiral, but if we're to draw an enantiomer, we can't. Because this chlorine is badly drawn as a line, and so we have no way of telling if that's supposed to be a wedge or a dash. So if we need to draw the enantiomer, we need to do the opposite of that. Since we don't know what it was to begin with, we can't flip it over. And so many textbooks kind of ignore stereochemistry later on. Well, the thing is, unfortunately, if it's the enantiomer, it has to have flipped every single chiral center. We're going to see we can draw a diastereomer that's a different type where we don't flip every single one, we just flip a few of them. So we cannot draw the enantiomer of this one. All right, so if you're going to draw an enantiomer, you need to have all the wedges and dashes. All right. I'll talk about this now, but we'll get into it more later. Remember before we had our cis and trans dibromo cyclohexanes? We're going to see we have relationships here. If I draw the enantiomer, of this one, I'm going to flip everything. So the wedge becomes a dash, and the dash becomes a wedge. If we're to draw the enantiomer of this one, they both become dashes. We're going to see that these two have a relationship as well. So the enantiomer means you've flipped everything. If you haven't flipped everything, if you flip one thing only, or everything but one thing, or 3 out of 5 things, so enantiomers you have to flip all your chiral centers, we see that these are what are called diastereomers. The blue lines. In fact, this is also a diastereomer that way. As is this. If we take a molecule and don't flip every single wedge and dash, we get diastereomers. So if we're relating things to each other, we have to look. Is every single chiral center switched? If yes, it's an enantiomer. If one center is switched and not every center, then they are diastereomers of each other. So, there are different relationships we have between different stereoisomers. Indeed, these are what we'll call meso compounds later, but that's the end. That's the most confusing part about this. We're not even going to worry about them. So they will in fact not be chiral. But that's going too far ahead. But we can still say they are enantiomers of each other, technically, if we really want to. But the important part here is that we have these relationships of diastereomers as well. So enantiomer, everything is flipped. Diastereomer, at least one thing is flipped, but not everything. So that's why. Like, for example, from going from top left to top right, I have switched the bottom bromine to be on a dash to a wedge. I've switched one thing, but not both. If I were looking at the top left to bottom right, I've switched the top wedge bromine to a dash bromine. And so, yes. It's fun stuff. Different terms here. Enantiomers, everything swapped. Diastereomers, not everything swapped. All right, let's learn now how the heck to even talk about these things. How do we talk about relating these by name to each other? For example, this pair of enantiomers they are different molecules, are they not? These are different molecules. And as different molecules, they have different names from each other. But they're both trans 1,2-dibromocyclohexanes, right? So, we're going to now replace that trans word with new ways of describing these. And we're going to be talking about, I forget what the rules are called, but we talk about R and S, or what is called absolute configurations. I think they're named after the scientists who came up with the system, but I don't remember. When we're looking at a particular molecule, let's take an easier example. Let's take our 2-butanol here. We saw that this had a chiral center. And how this is going to work is we are going to assign the letter R or S to this chiral center to indicate its absolute configuration. So that means no matter which way we rotate this molecule, by applying the same method, we're still going to get either R or S. It's one way of labeling it so that we know which molecule we're talking about. And how this is going to work is we have to assign priority to the groups on the chiral center. Or stereocenter. Remember, stereocenter, chiral carbon. I use all these terms for the same thing. Indeed, Kevin's already got the answer, and he's already explained it too. So priority is atomic number. So we are looking at giving things the higher atomic order, highest atomic number, higher priority. So if we're looking at this carbon, our first priority is going to be this oxygen. Highest atomic number. So oxygen has a higher atomic number than carbon or hydrogen. So we're going to see that that's going to get our kind of first priority. Let's just draw these. I'm going to draw our hydrogen in. Next, we have a hydrogen and 2 carbons. So hydrogen, we can say right away, is our last priority. The hydrogen there is our lowest priority because that is the lowest atomic number. But we have 2 carbons here. And so we go to first point of difference. So we're now looking here and here. They're both carbons, right? So we look, which of these carbon has the higher atomic number? Well, they both have 6 as their atomic number. So let's keep going. The carbon on the right has 3 hydrogens. So kind of the next atomic number is 1. Carbon on the left, though, has a carbon on it, which has an atomic number of 6. So that carbon on the left is going to have a higher priority. So we're going to say that that will be priority 2. And this one will be priority 3, the methyl group. So, first step is to assign priority. All right. What you want to do next, if necessary, it's not necessary here. We are going to rotate so that fourth priority is on a dash. So that means in the back. So you want your fourth priority to be in the back. In this case, we're already there, so we don't need to rotate this. And now we want to look at the circle in the order of 1, 2, 3. And so if I were to draw that circle on this molecule, we have, this is our first priority group. That circle goes this way, right? If we're drawing from 1 to 2 to 3, that circle is going counterclockwise. And here is where those letters come in. So clockwise is R, counterclockwise is S. So because this molecule has got a counterclockwise circle, we will label it with the letter S. The letters, by the way, come from Latin rectus, which means right, and the S is from sinister, which means left. So we're kind of looking at the top of this. We're going to the left as we start our circle. And so that means we are going with the S. So if we were to really name this, we would say that this is S. I'm sorry, we would technically need to put 2S. 2 or butan. We haven't learned alcohol naming, but that part now goes into the name. So it's going to work. Don't worry. This takes time. I'm going to show you another hint that we can avoid step number 2, because rotating can be tough. But we'll see. Yes. Let's see another example. Let's take a look at the R version of this. In this case, S is fine. 2S just indicates the number of where the substituent is. On the butane, you could get away with S2-butanol. Or sorry, S-butan-2-ol. You could get away with that because there's only one chiral center. But IUPAC, we want to be as precise as possible. So our alcohol is on carbon number 2 of the molecule, so we're putting the 2 with this. So either is fine. I'm okay if you just write S, but as soon as you have more than one, you're going to need to do the numbers. So this will be our R2-butanol. I'm sorry. I really just prefer this way. But will be very good. Okay. Anyways, how do we know it's R? Well, our priorities are the same, right? We have priority 1, priority 2, priority 3, and then now we have our hydrogen in the front. The second part of this says we are going to rotate our molecule, rotate along that single bond to get our OH to be in the front. So we can rotate the molecule towards us. I'm going to show you an easier way, by the way. If we rotate this molecule towards us, such that the OH is in front, we're going to end up taking our H that was in front, and now it's going to be pointing down. And now we're going to have our methyl group in the back. Our methyl group is in the back, which is still not what we want, because I totally should have rotated this the other way. Oh well. Not quite rotated enough. If I keep rotating this, I will now have my methyl up and my hydrogen in the back. If I keep rotating this, I'm rotating it kind of this direction. And now we can put our priorities on. 1, 2, 3. And if we draw our circle, we see that this is a clockwise circle. And so this is R. So you can rotate your molecule and then worry about it, but then you have to worry about how the heck do you rotate the molecule. And that can be difficult. 3D, it's tough to do 3D in your mind. So models really help here, by the way. I would definitely suggest busting out your model kit and working with it when you're looking at rotating these. That'll help you visualize it. But we have an easier way. If our hydrogen is not... Yes, the rotation is hard to picture. So I've essentially rotated this bond a little bit that way. That's very descriptive, I understand. So I've rotated that CC bond this way. So I've rotated my oxygen, which was pointed in the back, I've rotated it forward. As a result, now I have it on the front. And then I rotated it again. And now it's pointing down. So it was now in front, and now it's pointing down in the plane. So it's rotating around that ethyl group, yeah. So, tough to picture, but we have an easier way. Option 2 is you swap your fourth prio and whatever is on the dash. And then at the end, If you get R, turn it into S. If you get S, you turn it into R. So what we're going to do is we're going to cheat. We're going to say, okay, I'm going to just redraw this molecule, switch my H and the OH. I'm going to swap those two. And then I'm going to do my priority. And I'm going to see I get S this way. And since I remembered I switched it, I swapped the two, the H and the OH. I cheated. And so that means in the swapped molecule I have S, which means in our original molecule I have R. So if you switch two things on your molecule, you're going to switch your letter. So instead of rotating it, I just switched them. I redrew the molecule, swapped them. Essentially, I made the enantiomer. And then I just remembered, okay, my original molecule I did switch, so I have to switch my letter at the end. So this way I think is a little bit easier. It may be harder to understand conceptually, but it is practically easier than rotating the molecule. If you switch two groups, then switch your letter. That's all it is. And so as a result, the original molecule must be the opposite. So if the redrawn molecule is S, our original molecule must be R. So whatever your swapped structure gives you, your original will be the opposite one. So if you switch the two groups, whatever your fourth group is, switch it on the dash, whatever's on the dash, and then just switch your letter at the end. In my opinion, that's a little bit easier than rotating the molecule. I must say it took me years before I was able to rotate these things in my head easily without having to think about it. So I don't expect it will be very easy for you to rotate quickly in your mind. So that's why models help, first off. Second off, this method is a little bit easier in my opinion. All right, let's look at more examples. Let's see, let's do some. Let's see, what's some good examples? These are like boring. Okay, here's one. So, we have our dreaded triple bond, double bond again. Actually, I think... I don't want to do this. We'll add the methyl group later. So, because if we rotate the methyl group, we end up slightly more complicated example. And we'll do it. Okay, let's look at this. So, this one, the trouble is finding the priority. Priority 1, by the way, is the oxygen. Oxygen has higher priority than hydrogen. Hydrogen's, in fact, already on the back. That's going to be number 4. So we have 1 and 4 done. We have to choose 2 and 3, though. If you remember from before, a triple bond counts as 3. A double bond counts as 2. So, if we look at these, we are going to want to look at what's on those carbons. So, we see, okay, well, this carbon has 3 carbons on it. This one has 3 carbons on it. Yikes. Which means, I'll write carbons because that looked like cesium. So we have 3 carbons on both of those, right? We got 3 carbons on the left because triple bond counts as 3. On the right, we have a double bond, which counts as 2, and a single bond, which counts as 1. So 3 altogether. We now look at the next point of difference. We could look at either one, by the way. We could see that this is... Here, let me do this one in purple. Looking at the next point of difference. We see that this carbon is connected to 3 carbons and 1 hydrogen. So on the other side of the triple bond still counts as 3, right? This one also is 3 carbons and an H. This one down here, by the way, is just 3 H's, so who cares? And 1 carbon. We don't care about that. So that one's out. We're done with that one. And so we then go to our next one, which is going to be, we have now a third point out. The third point out here is a hydrogen. The third point out there is a carbon, right? So we're going to see that this side is going to win as a result. We keep moving away from our chiral center, and we're going to make our determination. So this is a carbon. That's a hydrogen. Carbon wins. So therefore, I realize this is slightly different from the one in the book, but that one's going to win priority-wise. It has the more carbons on it. Fun, isn't this? Anyways, now that we have our 1, 2s, and 3s, and our fourth one's already in the back, we're going to rotate. We see that this is an R. And of course, we're not going to be able to name this because we don't know yet, but this will just be an R if we're just looking at R and S. Fun. So just got to keep looking at your point of difference here with these molecules. So that's that. Let's finally go back to our best friends. I think I had this as a dash. Let's look at our friend here. Yeah. You guys don't know how to name that one yet. Oh, plus we also have easy... Never mind. With alkenes, when you're naming alkenes, there's more stereo things to deal with. Okay. So, these trans 1,2-dibromocyclohexanes, we're going to look at them next. Whew, exciting. 2 chiral centers, so we're going to have to do R and S for both of them. So, with the top bromine, that's going to be priority 1, right? Heteroatoms will have higher atomic numbers. Now we're going to look at these 2 carbons. Carbon on the top has a carbon and a hydrogen. Carbon on the bottom has a bromine. So that means priority 1 is going to be this one. And therefore priority 3 will be the other carbon. Hydrogen is in the back. We don't care about hydrogen. So we can go ahead and draw our circle. That circle is going to the right. So that is an R. That is a clockwise circle. So that one is R. I'm going to just redraw the molecule so we can mess with the stereo, with the absolute configuration more cleanly. All right. So with this one, priority 1 will be the bromine. If we're looking at this carbon, we look at our other carbon substituents. We see that priority 2 and 3 are going to be there. Remember, we need to rotate this such that our bromine becomes on a wedge and the hydrogen becomes on a dash. Or we cheat and just pretend this is a dash, wedge. If we do that, she's really snoring loudly. It's hilarious. Okay, if we pretend to switch this, now we can do the stereochemistry. We see this as S in the switched one, which means our original is R. So this one is also R. Do we see that? So remember, I swapped it so that the bromine was now on a wedge so that I could do my stereochemical or absolute configuration. When I switched it, I got S, which means the original dash bromine is R. So this is R and R. So we would call this molecule one R, 2R. We put these at the front. 1, 2. Dibromocyclohexane. So we put our locator numbers along with their configurations at the start, in parentheses, before anything else. If we had a methyl group on here, whatever, those don't matter. Like, you'll put your configurations at the very start of it. The enantiomer, by the way, will always be the opposite ones. So the enantiomer will end up being SS, 1s2s, of the same thing. So your enantiomer is always the opposite of your original molecule. So we're going to see that the enantiomer of our original molecule, which is 1R, 2R, will be 1s2s. So if we were to bother doing the S and R on the second molecule, we would see both would be S as a result. So enantiomers have the opposite absolute configuration as your original molecule. Diastereomers will have one thing or not everything switched. So for example, if you had 2s, 3r, 4r, 2, 3, 4 trichloro heptane. Just throwing out some random one. If we want, we can draw this. The enantiomer of this would be 2R, 3S, 4S. 2, 3, 4 trichloroheptane. Any other combination would be a diastereomer. For example, I could just switch the first one. Or I could switch just the second one. Or I could switch the last one. Or I could switch two of them. I could say 2R, 3S, 4R. So diastereomers, you can have all sorts of different combinations. There are more, right? It would be, we would have 8 total things. So we've got 2, we've got 6, so I need to switch the other 2. So 2, oh God, if I'm going to write them all out, why am I doing this? 3R, 4R, and then the last one would flip the last one. So we're going to have 2. No, we're flipping the first and third. Okay. 4S, 2R, 3R. Yeah, these would be all the diastereomers. So enantiomer, you have one pair. Everything is swapped. Diastereomers of this molecule would be any other combination where one thing or more is switched, but not everything. So Kevin had mentioned earlier your number of stereoisomers is 2 to the n, where n equals the number of stereocenters. So we have 3 stereocenters in this molecule, apparently. So we're going to have 8 total stereoisomers. Every stereoisomer has one enantiomer, which is everything switched. So our original molecule has one enantiomer, and it has 6 diastereomers. That adds up to 8. Original molecule, its enantiomer, plus 6 diastereomers will give us our 8 different stereoisomers. So we have 8 ways of arranging these spatially such that we get the all the different options we have here. So that's fun. All right, shall we try to draw this, by the way? Let's try and draw this, perhaps. But maybe we should start a little easier. Maybe we should start with just one thing. Let's start with something easier. Let's draw 2S, 2-chloropentane. Nope, not pentane. Gotta be butane. Pentane would not be chiral. I'm sorry, propane would not be chiral. Pentane would, but not propane. Okay, how the heck are we going to draw this? Well, let's just first see here. Well, 2-chloro-butane would look like this normally, right? And so, if we want to figure out if we need R or S here, the first thing we want to do is assign our priority. So we know prio 1 will be chlorine, 2 and 3. Hydrogen would be the last one, which would be 4. Cotton, stop it. That's just the wind. Relax. If we look at it drawn as is, if we say that this chlorine is a wedge, we get S. If we were to get R instead, we would know that we've drawn the opposite one. So when you're drawing your stereoisomer, just assume it's a wedge, see what letter you get. If you get the letter you want, then you're good. If you get the letter you don't want, just switch it to a dash. That's all it takes. So when drawing these, pretend The sub is a wedge. Do your absolute configuration. If wrong letter, make it a dash. So if we were to draw 2R, which is the enantiomer of this, we would have it on a dash. So if I wanted R, we would have gotten the opposite one, so we need to switch it to a dash. So this would be 2R. Poor Oz. All right. Can we please try this crazy molecule? The trichloroheptane? I think we should. I think it'll be great fun. 1, 2, 3, 4, 5, 6, 7. We have chlorines on positions 2, 3, and 4. I think. Yes, we did. Poor Oz and his reverse sneezing. Okay. We want this name. So let's just start on carbon 2 and make our way and decide the wedges and dashes that are going to be here. So let's assume we have a wedge on all of these things. And we'll just see what we get. And we'll see if we need to switch any of them. So if we start with all wedges, priority 1 will be our chlorine. Priority 2 will be our carbon that goes towards the other chlorines. And priority 3 will be to our methyl group. And so if we draw the circle, we are going counterclockwise. If we're driving a car, we're going left. Right? If we want to make a left turn, we would be turning counterclockwise. So left is S. So we're good. That chlorine stays on a wedge. Oh no, Capta39P9J9 has found us. Okay, ignore that as always. Okay, but we can have fun. Alrighty, let's look at the next one then. Priority 1 is the chlorine. Priority 2, let's take a look. We've got carbons with chlorines on them. However, there's a larger carbon chain on the right. So that's going to be our prio 2, our prio 3. We draw this. We are now turning right. We're taking a right turn in our car, turning our steering wheel to the right. And so we get R on that one, which is luckily what we wanted. And then finally, our last one, priority 1, is the chlorine. Priority 2, I'm going to draw this in a different color just because I don't want to overlap them. So priority 1 is the chlorine. Priority 2 is going to be the carbon with chlorine, right? Because carbon with chlorine beats carbon with other carbons or carbon with hydrogen. We're going to get this. So again, we are going clockwise to the right in our car, which is R, and miraculously, this was unintentional. We apparently have already drawn our molecule. So good for us. So apparently we finished it, so our answer is already done. However, if we had gotten the wrong thing on any of them, we would have just drawn it as a dash instead. So unfortunately, with these names, you can't just say, well, SRR, 2 of them should be on a dash, 1 should be on a wedge or something. No. In this case, all 3 are dashes. Enantiomer, all 3 would be wedges. All 3 are wedges here. On the enantiomer, all of them would be dashes. So, any questions on that? So if we're drawing it from the name, start with wedges. It'll be easier. Do all your stuff. See what letters you get. Once you have your letters, look at your original structure and say, okay, do I have all the letters I want? Or did I end up with one that's the opposite, or two that's the, whatever, however many that are the opposite, and then just adjust them as necessary. So flip them. If I wanted, say, 2s, 3r, 4s, that would be, I would need to switch it. And so that would be the one of the diastereomers, right? Is I've now switched one of my centers. So this would be that one, for example. As we did this, we saw we got R. We wanted S there, so now we have to switch it to a dash. All right, and so that's what we would get there. Same way, but with the 2-chlorine going up to begin with. Okay, so like this. Like that, Kevin? If you do this, you get, in fact, the enantiomer, right? Because this is essentially flipped over. This is a mirror image of my original molecule. So what we get here, if you were to do this, you get priority 1, 2, 3. Notice you get R here. We wanted S there. You're going to see if you do these, you get R, S, S. So you're in fact going to have the enantiomer. So what you're going to want to do is therefore switch them all. And so, in order to get the correct structure, this is what you would end up getting if you were drawing it that way. Which is the same thing as the original molecule. Or, I'm sorry, the molecule that I drew. These two are the same. So yeah, it totally just depends which way you draw it, right? Let me switch to vertical mode so we can see them both at once. But those two molecules are the same. And so that's the fun part about all this stuff. If you rotate the molecule on the bottom, the one you drew 180 degrees along the middle axis, you will see you'll end up with all your chlorines on the opposite side and on wedges. So you do get the same structure. So those two are the same. Isn't this so fun? So I have to be very careful when it comes to grading all of these. And so it's totally just fine to do it that way, Kevin. There's nothing wrong with the way you did it. We got the same answer, just rotated. And that's the unfortunate part about all this, is nothing is as obvious as it is in Gen Chem, where we just get a number at the end, we calculated our delta H and we're done. No. With these, there's always more thinking involved, so. All right. It would be a good idea to start practicing. I'm going to put up your homework. It's not going to be due for a while, because obviously you've got an exam next week that doesn't have this stuff. You should be focusing on your other stuff right now, but I'll put this up there if you want to start practicing. So I'll put up your stereochemistry homework. Okay, but that won't be due for a while. All right, I have got to head out now, so 12:15, we're done. I'm going to go ahead and put this up, and then we'll continue on this on Wednesday. All right, see you laters.